Nobody wants to do this. Come on, somebody, be great. Tell me. I got two theorists here and an experimentalist.
No one knows why,
we
right?
don't know why.
We know.
Hello, everybody, and welcome to Early Morning Coffee at CERN. My name is Stephen Goldfarb.
I'm Claudia Cornella.
My name is Kuberski.
And I'm Fred Gray.
And we have an amazing show for you today. It's something that is a result that really impressed me. We just had a presentation made last week, I think it was, on these results. And it might not sound familiar to you as a physics topic. It's from the Muon G-2 experiment at Fermilab. But the topic is really, really nice. And I think the thing that caught my eye was the degree of precision, the amount of work that went into getting this measurement. A measurement of the magnetic moment of the muon, which is weird. So I want to start out with that. I want to try to understand, first of all, to explain what is a magnetic moment.
Well, when I think of magnetic moments, I actually go back and think about bar magnets, the kind that everybody played with as a kid. And you know that some of them are stronger than others. Mm-hmm. And so the strength of a bar magnet reflects its magnetic moment. And, why is that magnet magnetized? It's magnetized because it's built up of a lot of subatomic particles, and the spins of the electrons inside all add up to the magnetic moment of the whole bar magnet.
Okay, there's a lot in that, okay? First of all, but a muon is just a simple particle, right? It's an elementary particle. It's like an electron, but more massive, heavier, right? There's electrons, muons, taus, those are the three leptons. I don't know, Claudia, maybe you can explain to us why would a muon have a magnetic moment?
Because muons have spin.
Uh-huh.
And if you want, to some extent, a spin is like a rotation, but it's not a rotation in a physical space. Uh-huh. It's really a quantum property of the particle.
Okay.
I don't know if that helps.
Well, I think it does a bit, but let me. First of all, we should acknowledge that this is the International Year of Quantum Science and Technology, which is in the spirit of our previous podcast. Of course, everything we do here at CERN, basically, or at Fermilab, has to do with quantum mechanics, quantum field theory. But that's a strange thing, though. You have to admit that's a strange thing. So an elementary particle, something which has no structure to it, you can't really think of it as spinning in space, but it has some property that's spin. I mean, why? And how do we figure that out? Nobody wants to do this. Come on, somebody, be great. Tell me. I got two theorists here and an experimentalist.
No one knows why,
we
right?
Don't know why.
We know that
it's
the case, but no one knows why they have spin. I mean, we just found out by the way they interact that there has to be this property that is like a tiny magnetic, like a rotation, but there can't be.
Right.
And this is what we have to live with. I mean, sometimes it's really just difficult and hard to understand, but it is. It's what the theory tells us.
But it is a really important property in the end, right? Because this is what defines the properties of material versus, say, the force carriers, right? Force carriers have a spin, integral spin, or in the case of the Higgs boson, zero spin, which is still integral, that's carrying the force. And then electrons and muons and taus and their neutrinos have spin 1/2. So there's a certain, that's the amount of spin they have. But I guess we learned about this because you can add that spin onto angular momentum somehow, right? You can add that on to that value. But okay, so this is somehow magically, this elementary particle has this property. And that gives it a magnetic moment. And how would you, with theory, tell me what that magnetic moment should be? What would you guess it would be?
Well, one thing to say is that spin is not enough in general to have a magnetic moment. Mm-hmm. In the case of an elementary particle, you also need a particle which is charged.
Okay.
Instead, if you have a composite particle, so a particle which is made out of smaller building blocks, that can have a magnetic moment also if it's electrically neutral. For example, the neutron is made of up and down quarks, which are individually charged.
Okay.
And you can imagine them to move a bit in the nucleus.
Okay.
So the charge distribution of the neutron, even though the neutron is overall neutral, has a non-trivial shape.
Okay.
And this, in combination with the spin, is what allows you to have a magnetic moment. So not every particle has a magnetic moment.
Not every particle is, but the leptons apparently do.
They all do, yeah.
They all do. So we have electrons and muons and taus. And why, maybe I can ask Fred, why did you guys at Fermilab, and first at Brookhaven, decide you wanted to measure the magnetic moment of the muon?
The muon is really kind of ideal because it has the perfect combination of mass and lifetime. So it turns out that if you're looking for the contributions of new physics to the magnetic moment of a particle, it helps if that particle is more massive. And the muon is about 200 times more massive than the electron. And that amplifies its sensitivity to new physics by a factor of about 200 times squared. And so that means, that it's a great laboratory for searching for new physics, but also, we have to have them around long enough to be able to study. So the lifetime has to be long enough. Of course, electrons live forever, right? They're stable particles. And the magnetic moment of the electron has been measured in the lab incredibly precisely, but it's not really so sensitive to new physics. Meanwhile, the lifetime of the tau is incredibly short. It's not long enough to be able to study it effectively. And so the lifetime of the muon is long enough that we can circulate them around. At rest, a muon lives on average a little more than 2 microseconds. In our experiment, about 64 microseconds, because they're moving at close to the speed of light, which actually increases their lifetime from our point of view because their clocks are running slowly. This is a really interesting thing from special relativity.
So there's a secret to longevity. Everybody, if you really want to live long, move really super fast. And this is why we know about muons, right? Muons hit us over the head all the time. Not to scare you, but while we've been talking, hundreds of muons have gone through your head from interactions in our upper atmosphere. And that was one of the things that got us started out on the whole path of doing particle physics, right? We saw Mother Nature's doing this all the time. I saw a calculation once that said that Mother Nature had done the whole LHC program about 10,000 times already in our upper atmosphere. So another reason to see that it's a safe thing. This has happened. We've done this, but we just didn't have our detectors around to measure everything that was happening at the time. But okay, so let's get back to the muon. And well, actually, we should mention this, that there's that lifetime, but the tau is much more massive. So that's the difference between these guys, electrons, muons, and taus. And it turns out that when you're more massive, as my wife tells me, you're going to decay more quickly. But it's true for elementary particles. The heavier they are, they have more ways they can decay in, right? Decay is a terrible word. I hate to use decay because they don't really...
Change?
Yeah, they change.
Transform.
They transform from one type to another. They don't actually... It's not like there's a muon. There's no electrons inside a muon, right? It's still an elementary particle. Okay, so you've made this really nice measurement. Not just you, your whole collaboration.
176 of us.
176 of you working on this all from the U.S. because it's in Fermilab?
No, it's very much an international collaboration with a lot of major contributions from places including Italy, Germany, the United Kingdom, South Korea, and China.
Wow, okay. So it's as international as many of our even larger collaborations that are here at CERN. And it didn't even start at Fermilab, did it? I mentioned Brookhaven. It started there?
Right. I would even say before that, it started with a series of 3 experiments here at CERN. And then after that came an experiment at Brookhaven that I worked on for my PhD. So I've been doing this for quite a long time now. We were taking that data back in the late 1990s, early 2000s. And we had an opportunity to relocate the experiment to Fermilab long after we were done at Brookhaven, because at Fermilab, they really had some great ideas about how to, with their accelerator complex, serve up an enormous number of muons to the experiment in small little batches for us, which turns out to matter. And so with many, many muons, because really our experiment is still limited by the number of muons that we've counted, by the statistics. And with them divided up so that they don't pile up with each other as they decay, so that we can count each muon decay separately. Wow. So that's the motivation for moving it there to Fermilab.
And that was easy, right? You just put it in a box and ship it, UPS or.
Well, when we first got started talking about the logistics, we were actually talking about picking it up with a helicopter and moving it with a helicopter to a barge in the port. It turns out the helicopter idea was not so practical, so it went on to a truck, to a barge, around the tip of Florida, into the Gulf, and then up through the rivers and up to the port of Lemont near Chicago, and then back onto a truck on the tollways in the Chicago area out to Fermilab. So it was quite a production.
I bet everybody loved the traffic jam.
I got to ride along with it one night, and you could certainly sense that at the closed on-ramps to the tollway, people were a little bit annoyed. But at the same time, I think it was worth it for the science that we got.
Sure. Well, I mean, we've been through that here. I remember taking my son to school. Actually, at CERN has a little school for when they're very young, and us being slowed down because there was a blue dipole. And my son at 3 was already saying, "Look, Dad, a blue dipole." So we've had that as when you do these major things, and when we build our future accelerators in the local areas, we'll have to make sure they understand it's a slight sacrifice, but it's worth it for the science that's being done. So I mentioned the amazing precision. And I think that's important to note here because I love to wax poetic about the experiment I work on. I work on the Atlas experiment, and it's an enormous thing. It's some half of a football pitch in length, and so over these sort of 46 meters, we also line up our detector at the far ends to tens of microns, right? So that means we have 1 in a million precision. Now, your measurement gives us a precision of what amount?
A little better than 140 parts in a billion. And so that is, the analogy that I've heard recently from one of my colleagues is that they have these big animals, a little bit bigger than cows at Fermilab, bison. They're famous. And so the precision is about 1 sunflower seed out of a whole bison.
Okay, so if a bison were to eat 1 more sunflower seed, you could tell the difference in that level of precision.
That's right.
That's a good definition of precision. I think the only experiment that beats us, I can tell you there is one that beats us, and that would be LIGO, right? Their measurements of gravitational waves. Impossible. I don't know how they do it. That's impossible. But you did a lot of work to get that far. But what I'd like to know, actually, I turn to theory now, okay? Because Simon's also working on trying to improve theory. This is a very interesting thing, because you guys have them beat a little bit here, the precision of the measurement. Tell us about that, Simon. What's going on? Why is theory not able to have a smaller error bar than the experiment?
I mean, the reason is not that we were not trying. So actually, I mean, before these guys built their experiments, there was this G-2 theory initiative. So really 100 of people from all over the world coming together with the idea that we should give our best to have really the most precise prediction of the theory, so really do the best doing calculations to be able to compare to experiment. And it was clear that we have to improve and that the experiment would be very precise, but it's an incredibly difficult calculation to do. So, I mean, the question is what is happening there? And the point is that at this precision we are talking about, everything matters, really everything, in the sense that this muon in the magnetic field doesn't only talk to the magnetic fields, which is composed out of photons, but there are all these quantum fluctuations. And it's really talking to all the forces in the standard model, which are the weak interaction, the strong interaction, and the electromagnetic interaction.
Okay, that's a strange thing. Let's try to wrap our heads around this for a second here. So everything's going on, right? You have a certain amount of energy. I know that if we take our protons and accelerate them, it turns out there's things popping in and out of the vacuum, out of nowhere. And perhaps the Big Bang was us just popping out of nowhere. I don't know. But that's happening, right, at high energies. So I don't know. Maybe Claudia, can you explain to me a little bit of how does this work? How is it that we don't get an answer that's precise? That's we have to sort of expand, I guess. How does that work?
Okay, it's complicated to explain.
It's complicated.
I'm gonna try.
Okay.
Well, in general, when we try to make a prediction for an observable, to make a calculation that then can be compared to the experiment, ideally we want to try to do it in the simplest way possible. Mm-hmm. And depending on the precision of the experiment, we need to get a certain precision on our theory prediction too. We kind of want to match that precision. Mm-hmm. If the experiment is not very precise, it might be enough to make we can call it some sort of approximation, which is good enough to get a prediction of the same precision as the experiment. But as the experiment gets more and more precise, mm-hmm. We cannot do these approximations anymore. Mm-hmm. And then things become very easily much more complicated. Uh-huh. Now, in general, depending on the type of interactions you're looking at, it might be possible that at every, if you want, difficulty step, the effect gets smaller and smaller. So by doing the first, we call order computation, you already get the bulk of the result. Mm-hmm. But what these guys in practice deal with is a situation where everything matters at the same time. There is no approximation.
Everything, everywhere, all at once.
Exactly, yes.
So what's going on here? So, I mean, it is a very interesting, because most people would think, all right, and it's very normal to think this, that you have a theory, and the theory will tell you, well, it should be 2. You know, that this is it. You know, you have a simple thing. You have a muon, here it is. It's got a charge and a spin, and you do your calculation. But it turns out, because of the energy, that things can pop in and out of a vacuum. You end up having to do, and this is what actually drew me into the field, I have to admit, in quantum field theory, was that when you have an interaction, there are a lot of different possible things going on. Right? So I always mention this when I talk to people about what goes on when we collide protons, and these 2 quarks, let's say, or 2 gluons interact. There's many different ways that can happen, and we're not even allowed to see that, right? We never know. So you guys never really get inside there and see what exactly happened with this muon becoming an electron. And it could have gone through many different paths, some of those very complex, but the more complex they are, the smaller the probability, and some of them straightforward. And you end up with this sort of infinite sums, right? You get something that we learn. If you go far enough in math, at school, you'll find these sort of expansions, and there you see that the bigger the further you go, the smaller the numbers are. But as you're saying, in this world, in the world of the muon here, you have to go out pretty far to get the precision. And Simon's just not getting it done.
No, it's really complicated. I mean, so there's the frustrating thing maybe is that 99.99% of this theory prediction is based on this electromagnetic interaction, and people can compute it very nicely, and it's super precise. And then there's a small piece, it's called the hadronic vacuum polarization contribution, and that's basically, I mean, there's the muon, and then there's a photon that tells the muon how strong the magnetic field is, and then this photon makes a quark-anti-quark pair, and as soon as we have this, everything happens. There are tons of particles, and everything happens at the same time, and we cannot just sit down and write a formula and get to a result, and we cannot even go to a computer and press a button and get the result. So we have to go to a computer, but it takes years and years, and the biggest computers in the world to get to results that we have.
To understand this sort of, there's a name for this, right? Lattice QCD?
Yes, it's called Lattice QCD, and it's really the only method that we know that reliably can tackle this strong interaction, these hadronic properties of a theory.
Yeah. So just to recap, I mean, the strong interaction, for some reason, there are people out there who don't know about QCD and the strong interaction. They ought to. And that's, the interaction between quarks. Quarks are what we put them together, we make protons. where we make neutrons out of them, and there's a whole lot of other hadrons. Our friends at LHCb are finding new combinations all the time, pentaquarks and all these different things, or excited states of these. But in this case, you can produce these pairs, and when you do that, lots of different things can happen. So I guess, I should note that we had to bring on 2 theorists because the experimentalist has done his job over there.
And the theory is really more than twice as hard, I have to say.
Yeah, okay, it is. It's a very hard job to try to get this down. And one thing that's important to note is at no point are either of you guys trying to be like the other, right? So you're not saying, oh, my result is over here. And for a while, it's been like that, right? The result of the measurement has been a little bit a ways from theory, which makes it intriguing and interesting. But all you're trying to match up is the precision. Try to get as good a precision or better than the other, and then you'll see what nature tells you if they agree. So maybe, Fred, you can expand a little bit more on how, because you guys did an amazing job to get the precision that you have. What did you have to do?
Right. Well, the first key was simply measuring an awful lot of muons. So we recorded a little more than 300 billion final events that made it into our final data set. And to do that, we actually had to store more than 1 trillion muons in the storage ring. So that was really, the first key was simply having this incredibly high statistical power. And then we really had to pay attention to, like you said before, everything everywhere all the time. So we had to focus on really improving every possible systematic error. And you can see going from one year to another, the kinds of things that we improved. So for example, our experiment, the technique really relies on what's called the magic momentum, which is to say that the muons have exactly the right momentum that the electric fields don't rotate their spin, so that we can use large electric fields to confine and focus them inside the storage ring. And yeah, on the other hand, not every muon is going to have exactly the same momentum. Some will be going a little fast and some will be going a little bit slow. So for this most recent result, we just had to work much harder on measuring the distribution of momentum, including building a whole new detector like some of my colleagues at the University of Washington did, and they call it the mini sci-fi. And so we introduced this in order to get just that much better precision on what we knew about the momentum. And, you know, for example, we need to know the magnetic field incredibly precisely that the muons experience. And so there we've been measuring the magnetic field in a sort of static way. So the part of the magnetic field that doesn't vary with time by pulling a trolley full of magnetic field probes all around the inside of the vacuum chambers at a time when the muons aren't there. But for this most recent measurement, we also were able to measure the time-dependent magnetic fields from when we fire the kickers that kick the muons onto the correct orbit, and from when we energize the quadrupole plates that make the big electric fields that confine the particles. So, you know, very precise measurements of those things were included progressively as we moved from the analysis of one run into another to get to better and better precision. And we're at the point now where really we would again have to improve everything if we wanted to continue to make progress here. We've really gotten those systematic errors down as small as we practically can.
Yeah. Okay. I mean, that's so. There's a few technical terms I should mention here. Kickers, for example, or quadrupoles, but these are all sort of means of using electromagnetic fields. You have an electric field to push things along and make them go at higher energies, and then your quadrupoles also will. Do they focus or they?
They are for focusing. That's right. And actually, we don't have anything that that changes the energy of the particle once it gets into the storage ring. The kicker just redirects the particles from an orbit that would come around and hit the injection point again onto an orbit that would be stored in the vacuum chambers that you know, sort of centers it right in the middle of the quadrupoles.
Okay. For those watching, actually on YouTube, we do have a picture of it. It's a relatively small accelerator compared to what you see here at CERN. Usually.
14 meters in diameter.
14 meters in diameter. But it's an amazing thing. And actually it has an interesting part to it. I noticed that when the muons come in, there's like a gap, right? There's like a space between the magnets, and that's fine. Muons just keep going, right?
Right. Over a short distance, that's certainly true, although over a long enough distance, you certainly want to have them in a vacuum so that they don't scatter off of the air.
Beautiful. It's a beautiful, beautiful experiment. And congratulations on getting such amazing results. I do want to go back to the slight discrepancy that there was, and maybe it's disappearing, we don't know. What can we learn when we do a precision measurement like this? Maybe I'll ask Claudia, if you do a precision measurement, how does that help us when we compare it to theory? What can we gain from that?
Well, whenever there is a discrepancy in a precision measurement, especially if this discrepancy is statistically significant, like it was in the case of the G-2, we as theorists, all we want to do is to try to find out which type of new particles and forces could explain that discrepancy. So precision measurements are the perfect venue to do this. In some sense, by looking at a discrepancy, we can learn several things. We can learn something about possibly the scale, the mass of the particle that explains the discrepancy, and also something about its coupling.
Okay, coupling being how they interact?
How they interact, yes. So for the case of the G-2, two of the most common explanations were one in terms of very, very light particles called axion-like particles. These are particles that arise, for example, in models trying to explain dark matter or to solve another big problem of the standard model, which is called the strong CP problem. Or also other types of particles, like, for example, heavy bosons, like heavy Z bosons, that couple differently maybe between electrons and muons and taus, etc. Then in practice, when we build one of those models, we also have to pay attention, because in general, the moment you have a new particle with new interactions, it's not just going to pop up in one measurement, but it's also going to arise somewhere else. And then you have to make sure that your model doesn't contradict other data. So somehow from these small discrepancies, if they are confirmed, if they are statistically relevant, we can definitely learn something about what is beyond the theory that we know right now. So, and we know that there is something beyond it, because there are several problems it doesn't address. Exactly.
And that's it's important to note that we have this amazing theory, and we keep testing it. And we'll be doing many more precision tests here. For example, at CERN, we're always doing precision tests as well. We're not just looking out there, is there a new particle out there? We do that, and we love that. But we will be, in fact, in a year, tearing apart the LHC in our experiments. At least Atlas and CMS are going to be refurbished to go to high luminosity, and in which case, when we get many more collisions, just like you need lots of muons, we need lots of proton collisions. And with that, we get the higher statistics, we get higher precision, and we can look for very rare things, but also look for these discrepancies. Because we're missing, 95% of the universe? The standard model's great, everything like this. And then in the future, there are many different ideas out there of what we want to do in the future beyond the LHC after I've retired, for sure. And that, includes electron-positron colliders, maybe a huge FCC, maybe linear colliders, also possible muon colliders. For those of you in the muon business, a lot of different ideas out there, but precision is one of the things we really want to look for. So before we finish up, actually, I would like to hear a little bit more from Simon about, what are the next steps? You mentioned getting more computing. That's everybody wants that. ChatGPT will work better too with more computing.
And we can use the same computers as the ones training ChatGPT.
Oh, okay.
So it would be great if they just hand it over to us.
Hand them over to us.
Hand it over, yes.
Ask ChatGPT, could you hand over? But beyond that, what else? What other work can you do to improve these models? What work is going on?
So really, I mean, there are two ways to compute this HVP contribution that is really carrying all the uncertainty. And Lattice QCD has only recently, I mean, in the last 5 years, we were able, to reduce our uncertainties by a factor of 5 or so. And now we're really able to make this prediction. And we're very certain that we can improve. But as Claudia said, as soon as you want to get to better precision, you always have to be more careful about tiny effects that you have to control. So it's certainly getting bigger computers, getting better algorithms. I mean, be smart about how you want to compute something and also have new ideas. And then there's a second way one can compute it. Has been done historically. It's called the R ratio method. And they can also improve with new experimental input, actually.
Okay, because sometimes a theory has to have for various values that you use for the input. Okay, before we go, one last thing. I'm going to turn it over to Fred here. What's next? You said you're not going to do it yourself, right? Are you handing the baton over to anybody else?
So at Fermilab, we still do have a few more papers to come out of our experiment. So we're going to look at the potential for new physics to cause our result to change as a function of time, maybe oscillating, getting a little bigger and smaller over time as a result of coupling to things like dark matter fields or violations of the postulates of special relativity. So we'll be looking for that. We'll be looking for the electric dipole moment of the muon. We should be able to set a limit that's stronger than the current limit on how big that could be. Should be 0 in the standard model. So if we were to see something that's not 0, then that would be exciting. But then the next Muon G-2 experiment is going to be at J-Park in Japan. And they have a technique there that is like ours, but with muons that are not at the magic momentum. So they can't use electric fields to confine them. Instead, they cool their muon beam to the point where they don't have to use electric fields, and they can use a much smaller magnet. So they will be able to do a complementary experiment with smaller uncertainties. I should also point out that the reason that I'm here at CERN is to work on an experiment called Muon-E that we're setting up at the CERN SPS. And so what we are doing there is getting experimental input for a third way of doing the theory. So you've heard from Simon about 2 ways, right? From electron-positron collision data, the R ratio method, and lattice gauge theory. Well, we're observing the hadronic vacuum polarization effects in the interaction between a muon and an electron when a high-energy muon beam hits the electrons in a target.
Oh, okay. Great. So I should say SPS, by the way. Many people might know that, super proton synchrotron, which brought us the W and the Z boson many years back, about 1983, I think it was, way, way back. And we still use these. And we have some older accelerators than that even that we still use as well. Well, thank you very much. Fred Gray is professor of physics at Regis University in beautiful Colorado, I think it is. And Simon Kuberski and Claudia Cornella are both fellows here at CERN working in the theory division. So thank you for joining us. This has been Early Morning Coffee at CERN, a podcast by the scientists of CERN, or not just CERN, and about the science of CERN. You can find all of our episodes on the CERN YouTube channel and anywhere you get your podcast. Guaranteed. Go ahead. Find the place you get your podcast. You can find us. Be sure to do whatever you're supposed to do. Like and share and, send it to your friends. There's a lot of things you're supposed to do. So do those things and subscribe. Our editor and producer today is Melanie Arnold. Hi, Melanie. Good job. Thanks. Our executive producer is Jacques Fichet. Jacques Fichet and Piotr Traksik, also known as Jesus on occasion, are our technical leads while Ron is away getting fixed up. Our studio manager is Max Price, and sound engineering is by Piotr Traksik. Our original theme comes from the Knetz Blues Band with piano by Wojt Play It in Any Key Krajewski. Many thanks to Paolo Catapano, Matthew Chalmers, and Arno Morselier for all of their advice and strategic planning. A big thanks to the entire education, communication, and outreach team here at CERN for providing us with access to beautiful wire chamber studios and all the help that comes with it. I also want to take a moment to thank Chetna Krishna, who's no longer with us. That sounds terrible because because she finished up her fellowship here at CERN. She, along with Joni Pham, were really two of the people who came up with the whole idea of doing this, and I get to have a lot of fun, and I hope that they're doing well as well. Opinions expressed here are our own and do not necessarily reflect those of our colleagues or of CERN, although we think they ought to. My name is Stephen Goldfarb. This has been Early Morning Coffee at CERN. We'll see you next month.